So traveler gets lost in distributed Poisson lambda times on the long journey. When this traveler is lost, he asks for directions with probability p. And we're letting x be the number of times that the traveler is lost and asks for a direction. And y is the converse. So here we are asked to find the joints PMF of N, X, and Y. And also asked if they are independent. And because we know that N is defined as X plus Y, so this is deterministic relationship between N, X, and Y, we can immediately conclude that they are highly dependent. The joint of these three variables can be factorized into the following. We're choosing this factorization because we know when we condition on n, like we do right now, what x and y are. Okay, and so this factorization basically yields that once we know n, x and y are the same events. So knowing the number of times he asks for direction, we know exactly the number of times he doesn't ask for directions. So we can drop one of these terms, and we end up with probability of x equals n, like so. And now we know that once we condition on n, that x is distributed binomial with probability p, and so we know that conditioning on n, like so, is binomial p n, like so. Okay, and so this means that we have n time n, choose x, probability of x, q, probability of n minus x. We know that this term is Poisson, and so this is lambda n e to the minus lambda divided by n factorial. That's the definition of the Poisson PMF. Okay, and then we can rewrite. We have n factorial, x factorial, n minus x factorial, p to the x, q to the n minus x. And we can write, and we have times lambda n e to the minus lambda n factorial. Okay, and then we see that the n's cancel, like so, and we end up with some terms here that can be rearranged to all be written in terms of two random variables, which is x and y. And so I'm going to collect all of the terms that belong to x, and then all the terms that belong to y. And here, observe that this term here is just y factorial, and so that we can put here y factorial, and then we have this is also y, so we have q to the y factorial, and we have n being equal to x plus y, and so we have a lambda y factorial, no factorial there, and then lambda x, and then we have exponential y lambda p exponential y lambda q. Where did the p and the q come from? Well, we have actually times 1 here. Times 1 is, and 1 is basically just p plus q. So here we end up then with the PMF of the joints equaling the same thing as the probability of x, so the marginal of the y's here. Okay, so that's the first part. Now the second part, here we asked to find the joint PMF of N and X. Okay, so the joint part of N and X here can be written as the okay, and so B here N equal N, X equal X, like so. Okay, and this is the same thing as marginalizing over y of the joints of N equal X like so, y equal y. Okay, and here we could, I mean, this is actually quite important, which is that if I would say, well, this joint here is actually what we just solved up in problem A, and so this whole thing boils down to the following, right? And then we would, you know, just basically replace, and this, I'm going to say this is wrong. I'm going to replace this joint as, and then we have the sum over y, and then we have the probability of x equals x, probability of y, and then we would say, oh, look at this, you know, this sums to 1, and then we end up with something that equals only probability of x. This is wrong, and it's wrong for the reason that y is only, this sum is only true, well, it's actually true for all terms here, and I'm going to write it in the following way. So y equals 0 up to infinity. This sum doesn't sum over all y's, so this will not become 1. What we have here is that we're going to select, you're going to select two numbers, you know, n is equaling to something and x is equaling to something else. So, you know, n could be equal to I, and, you know, x is equaling to something like j. And so y will only be, this term y will only be true for one specific event, and that's when n, well, let's just call this, to be very explicit, it's n is now I, so I, and x is j plus y here. So that will only happen for one number, and the rest is the rest of this probability, when we sum over it, will become zeros. So we end up with one number, and that number is I'm going to do the following, just to be very explicit. This thing here I'm going to factorize in terms of n equal, and then we said, you know, we have I, x equals j, and the condition on y, y equaling y, probability of y equaling y, like so. Okay, and this is only true, this will only true, as I said, for one specific event. And so what we have here is this sum disappears, well, disappears in the sense that it's 0 for most of these terms except for one. So we end up with n equaling I, x equaling j, this y is like so, and then we have this equaling y, okay? And y, right, and then what we have here is that now we have these two terms will be this conditioning on y. We know that these terms will be the same term. So we can basically drop one of these terms, and also we know what this y has to be. That y has to be 1 minus j. Okay, and so what we have then in the end is x, probability of x equaling j, conditioning on y equaling I minus j, y equaling I minus j, like so. Okay, and we know also that given this situation, that the marginals are independent. So we end up with that we know also this x is a Poisson probability with Poisson with parameter p lambda, and this thing is j factorial e to the minus lambda j times I minus j factorial e to the q lambda, and then we have q to the lambda I minus j. And so this is basically saying that this whole thing boils down to two independent random variables, Poissons, with the parameters defined by the shape of these terms here. Okay, and so the last exercise, we're going to find the joint of x and y, and we basically have already done this, but we're now doing it in a we did this in exercise 60, but let's do it again. And we're going to basically follow the exact same logic. We have the probability of x equaling x, y like so, and we're going to we have to marginalize over n, and y like so. We're summing over n equaling from 0 to infinity. That's the support of the Poisson. And with the same logic that we're selecting x and y to be specific numbers, so this sum again will only be true for whenever n equals x and y, and these x and y's have to be selected, and they are a, b specific numbers. And so we end up with the probability of x equaling, we'll say this is a, and that specific number again b, well then n is equaling just a plus b, n equaling a plus b, and again these two things here are the same event, and so we end up with, we can drop one. Let's drop y. A plus b like so. And then we know that this is a binomial, and that's a Poisson. And so what we have is N, choose A, P, A, Q, and then we have N minus A times the Poisson, which is lambda A plus B, exponential E minus lambda A plus B factorial. And this thing here will again just boil down to the probability of X times probability of Y. It's just for the sake of completeness, continue ahead here. Probability of A, and then we have A factorial and minus A factorial. And then we have Q and N minus A here is just Y. Well, that's not Y, we just called it B, so let's call this B. And so we have Q B like that, and then we have lambda A, lambda B, e to the minus lambda P times Q. And that all divided by M factorial, right? This thing here is N, and that's a factorial. Okay, we can, whoops. Write that, and let's just rearrange everything. So we have here, we have a B. So we have a, let's collect all the terms that belong to A. Lambda A, e to the minus lambda P. And then the same thing here. Lambda P. And then we have a Q term here, like so. And then we have the Q to the B. And these indeed are the two random variables, x equaling x times y equal, well, it's not A, but it's actually one specific A and B, right? Those are the ones that we had to select. And that's it. These are two Poissons. So the whole thing here just boils down to two independent random variables.